Hey, welcome to this video presentation about our recently accepted paper, Robust Weight Imprinting Insights from Neural Collapse and Proxy-Based Aggregation. My name is Justus Westerhoff, and this is a joint work between the BHT and the HTW in Berlin. On this slide, you can find a link to our code and to the open review, and also exactly to these slides, which also the QR code leads to. One caveat maybe, this is only of course a teaser of the paper. There are much more details in the paper. And also I want to express my dearest thanks to the TMLR reviewers and also the action editor for their feedback that greatly improved this paper. Okay, so some motivation. In this image here you can see a model, this green brain-like thing that was trained on some data. And now the question is, if we have some new other data, for example, handwritten digits here from MNIST, how much can this model still do with this other data, with this out-of-distribution data? This question comes up in many fields like few-shot learning, transfer learning, continual learning, where you want to see if you can make a model work on classes that it has not seen so far. There surely come much other problems along with that, like catastrophic forgetting and continual learning. But here in this paper, we want to focus on how can we directly from the data transfer new knowledge and consolidate new knowledge about new classes. And we will specifically target the classification head of a neural network, so only the last layer weights. The paper in which the term imprinting first came up was this seminal work here, Low-Shot Learning with Imprinted Weights by Chi, where what they do is simply imprint a mean. So if they have data of a new class, what they simply do is they take the mean of the embeddings and save this mean to the last layer weights, so that they can then also classify this new class. Right, and this kind of mean, we could also say this is a proxy, because this will then be the proxy for the new data. In this paper, they are inspired by human vision, so to say, because humans have the ability to learn new categories from very few examples, which is called the area of low-shot learning. And we have the restriction here when we talk about imprinting. We mean doing that, but without storing or caching data, without relying on any cross-class statistics, so I can only see each class one by one after another and cannot store things in between. And we don't want to use any gradient-based optimization. Rather, we want to set the weights from the data directly. Since this work, imprinting has been applied to a whole lot of other fields like object detection, multi-label classification, semantic segmentation, and many more, whereas Chi specifically targeted classification and the last layer weights, which we will also do in this paper. Open questions still remain. For example, how important is normalization of the embeddings or of the proxies you generate? How actually do you generate these proxies? Do you simply take the mean, or what other ways could you do? And also, how do you aggregate these proxies? If you would have only in the end one proxy per class, what you usually do is you take the maximum activation, so max, but you could of course also think about other things like nearest neighbors, where you compare your new embedding with the maybe many more proxies that you have per class and compute some nearest neighbor. Imprinting has also been applied in the industry already. For example, there's Google's Coral Edge TPU, which includes an imprinting engine API. And you can also think of other scenarios where shortage on data storage or shortage on compute, for example, for security reasons or for practical hardware reasons like battery-powered edge devices where you can't frequently retrain, that these are areas where imprinting can become really helpful. And maybe final motivation, why would imprinting even work? Well, if you have a model, a neural network, and you train it on some classes here on the left, the gray classes, then the network typically experiences neural collapse, which means that the embeddings, so the last layer weights, and therefore also the embeddings of every class, collapse to their class means. If you then take new data, for example, from a new task T, we call it in the paper, then these classes are probably not collapsed, as you can see on these brown and pink blobs, but they still have some structure. And we want to find out how good can we do imprinting, how do we choose our proxies to remember this new data, to perform transfer learning. That's why we come up with this framework, because we've seen in a lot of works, people try out different combinations, different settings, but they are never really compared. That's why we have this framework, which we call IMPRINT. There's essentially 5 variables in this framework. There's the normalization before the weight generation, normalization after the weight generation, the normalization of embeddings in inference, and also aggregation. And all these variables can take certain values. For example, in the paper we analyze, what if we chose k random proxies? What if we compute the mean as Chi does? What if we use k means or k metods to compute the proxies from our given class data? Or what if we choose those that maximize covariance, or those that are farthest away from points we've seen before, like farthest point sampling? There are all these kind of heuristics you can think might be something the brain would do, and we try all these out. Also, we test different normalizations. For example, L2 normalization, but also quantile normalization, as was first done last year in an imprinting-like paper. And we also check the impact of the aggregation mechanism. As I said before, you could just take the maximum activation, or you can even perform an M nearest neighbor on the proxies that you have generated. And in the paper, we investigate all these aspects of the framework in great detail. Here, I just want to present you the main findings. First of all, we can refine previous work from literature, like the one from Chi, Hosoda, or Jensen, within our framework, because then they just become a very special combination. For example, Chi is mean weight generation, all normalizations are L2, and max aggregation. And the accuracy it reaches across our tasks, which we define through varying foundation models. There are 4 foundation models and 12 different tasks, and here you can see the average accuracy, which is like 86.79. And you can also see the other methods, for example, Hosoda, who uses quantile normalization, or Jensen, who uses a 1 nearest neighbor aggregation. Well, and then in IMPRINT, in our framework, we just simply test out all the variations that there are, and we conclude that if you use k-means, so you have multiple proxies per class, in this case k is set to 20, you can reach a much higher accuracy. And it's still imprinting, because you're still doing it class by class. You're not using any cross-class statistics, and you are also not performing any gradient optimization. Also, you're not storing any data. We also have an Oracle baseline in here, which is kind of least squares. So you can think of this as the optimal method of computing your weights. This is, however, not an apples-to-apples comparison, because least squares needs to have all the data of all classes at once, so it uses cross-class statistics. Specifically, you compute the covariance matrix, right? What this table shows is that our method, which is an imprinting method, significantly bridges this gap between, you only imprint the mean and you perform this super good least squares or gradient descent, and we cannot bridge this gap because we increase by more than 4% on average. Throughout the paper, we always also show critical difference diagrams, which you can see here at the bottom. It makes sense to evaluate these different classifiers or methods using ranking aggregation, because as you can see, the standard deviation is very high, which is expected because the tasks are very heterogeneous in difficulty. Sometimes it's just imprinting 3 classes, sometimes it's 10, sometimes it's from a ResNet 18, then it's from some vision transformer. That's why we always use critical difference diagrams to show the significance, and we can see here that this new method is significantly better than all of the ones before. Right, then it's also interesting to look at this again from a low shot point of view. What if you only have a few samples for the new classes you look at? Because previously that wasn't really bounded. We were just asking the question, okay, you have a given foundation model, it's frozen, here's a new class, new data. Now use the data directly to learn new weights, directly from the data, class by class. Here we look at the same question, but we also limit the amount of data we have. And interestingly, we can see that this teal blue curve, k equals 1, which is imprinting the mean, so having 1 proxy per class, it gets outperformed at already roughly 50 samples for datasets like MNIST and Fashion MNIST. Because there you can see that the purple or even the pink line, which uses k-means proxies, so k equals 5 means you generated 5 proxies per class using k-means, likewise for 20, that these curves, they outperform the blue curve starting at around 50 samples for MNIST and Fashion MNIST. On Cypher it's a bit later, which makes sense, and we also see this in the next slide. We also compare here to k equals n, which means storing all data. So each data point that you see becomes a proxy, which you could think of as overfitting, which it is, because you can also see that the performance is much worse. All right, so much about the low shot scenario. Now I want to dive a bit deeper into neural collapse. We've already seen this teaser image, which I show again here in the top right. Neural collapse means that the learned embeddings or the learned last layer weights, which is analogous, of a neural network collapse to their class means. There's a more precise definition that they collapse even onto a simplex equiangular tight frame, ETF, but for that I would again reference to our paper. And there's a measure for neural collapse, which is NC1, and you can think of this simply as the within-class variance divided by the between-class variance. To artificially control the neural collapse of datasets, we come up with new ones, which we create directly from ImageNet. What we do is simply, combine multiple classes into one class. For example, if D equals 5, that means this is 50 classes from ImageNet, but we always combine 5 classes into one. So in the end, we still have 10 classes, but each class originally consists of 5 classes from ImageNet. And in this graph here, we can nicely see that for all the foundation models that we test, for all these pre-trained models, the NC increases linearly when the D, so the number of classes we combine in one, increases. This is very much expected, right? Because the within-class variance, of course, greatly increases. The between-class variance is not so sure what happens to that, but at least the numerator increases, so the NC1 increases. And with that in mind, we can dig a little bit deeper even and look at the effect on performance if we choose a different number of proxies. In these red to yellow colored curves, we again see these artificially made up ImageNet datasets. On the x-axis, it's the number of proxies we generated, again using k-means. And then the dashed lines are, again, other datasets, not ImageNet, but from kind of our test. So MNIST, Fashion MNIST, Cypher, also combi digits, which we create in the paper. More information about that in there. What we can see here is, interestingly, but also expectedly, that the best number of proxies to generate equals exactly the number of D. So you can see the little peak there always in these red to yellow curves, which always happens at k equals D, right? Because there's 5 classes combined into one. So it probably makes the most sense to use 5 proxies to represent that data. And then these dashed lines, you can see that, for example, for Cypher, because it might be very similar to ImageNet, you don't really see a lot of increase when you use multiple proxies. But for MNIST and Fashion MNIST and also combi digits, you do. Putting that into even larger context, together with neural collapse, we can produce this graph right here, when on the x-axis we have the NC1 score, which I mentioned before, and on the y-axis we have the increase in accuracy when we take 5 instead of just 1 proxy, again always using k-means. What we see here is that there's first of all like a positive relationship, and this is also statistically significant. The R-squared is 0.36, but the Spearman rank correlation rho is 0.82 across all points, so we have a statistically significant positive association here. The higher the NC1, the more the increase in using more proxies. Especially we can see here that in these regimes of high NC1 greater than 1, that the single proxy mean imprinting appears to become substantially suboptimal, because we can see that there's an increase in using multiple proxies already like above that, more than 5%, just by using not only 1 proxy but 5, just by using 5 means instead of 1 mean. Right. What else is there in the paper? These were just the highlights. As I said, in the paper you can find a much more thorough analysis of each component within IMPRINT. You can also find an extension of least squares where we thought about how we could combine this with k-means, and then we also compared with mean, k-means, and least squares. We also have a runtime analysis. We have a more theoretical view on imprinting as memory. And there's also some details about the differences between these different foundation models, mainly CNN versus transformer-based. And with that, I want to thank you for your interest and for your time. I hope that you have now even more interest in reading the paper. I'd really invite you to take a look at it. I also want to thank the DFG for funding this and making all this possible. You can see my email address here. If you have any questions, please reach out. And thank you very much for your attention.